so we can keep track of everyone who's, set up on. Yep, just put it in the chat. Okay, without any further ado, it's a fun lesson ahead today. Lesson, that sounds like a professor. Okay, hang on. All right, we good to, oh no, oops, you weren't supposed to see that. We good to go? Is this thing recording?
Yeah, it's recording.
It's recording? Okay, cool. All right. Hello, everyone. My name is Rohit, and I am one of the three project leads in our club. I am the AI lead. Thank you to everyone who joined today. And it is exciting to get going. This is Introduction to AI. It's the start of, the next few weeks of just working with AI concepts, as well as building up like a little bit of basics so that, when the project comes around, you guys kind of know what to expect. And it's going to be fun. Even if you don't understand everything today, there's no problem. First of all, we're going to be putting this up on YouTube as well as sharing the slides, but we'll give you resources, and you can always hit us up offline outside meeting times, and we're happy to talk. So with that being said, can anyone tell me what I'm thinking of with this number in the chat or like on your mic? What could I be referring to with this number?
Money you're going to give me?
All right. No, I'm sorry to rain on your parade, bro, but that is not it.
Just kidding.
That would be cool. Any other guesses? What could I be referring to with this very particular number?
As neurons in the brain.
Oh my goodness! Wait, who said that?
Vivek, I just googled it.
Dude. Oh, okay, but that's pretty cool. Oh no, oh man, I hate accident. Yeah, whatever. Okay, that is really cool. Good job. Good guess. I don't know if that's a guess anymore, but yeah, it is the number of neurons in the brain. And it's like a sign of how many little units we have inside our head that are doing thinking, right? So we are a pretty complex biological organism. That is one great example of it. What is the best site to learn Python? I'm sure Samrat, the Python lead, would be happy to have a discussion with you about that. Okay. All right. So who am I? Before we get started, just to get this out of the way, I am the AI lead at BigTh AI. I interned at an AI product firm. So I worked on 2 projects. One of them, I was just kind of there in the room, watching presentations about what they were doing. They were helping a customer figure out, okay, wait, we'll get to what they were doing later as an example. And the other project that I was doing had to do with building an AI to play like a 2D game that I had created. So that is my industry related experience so far with AI. I did some independent research, went through like a ton of research papers. I did a 5-course specialization by Andrew. And if you guys have heard of him, he's a pretty famous researcher on AI. He's from Stanford. I'm a math guy, right? I love math. I'm not always the best at it. I don't claim to be, but I just love math because it's really satisfying. I don't know if that's a popular or unpopular opinion, but yeah, I am not an avid coder. I'm a computer science major, so I kind of have to code, but I am not a coder by trade. I picked it up just so I could employ math in something as exciting as, AI, and using these tools like AI and ML to draw solutions out of data. So that's what I refer to by not an avid coder. And I do not claim to be an expert. I am not a teacher. I am none of those things, but I'm just someone who's willing to share whatever little I've seen and, learned about AI with you guys so that we can make the semester fun for everyone. This is one of my favorite tweets, by the way. A CPU is literally a rock we tricked into thinking we had to flatten the rock and put lightning inside it. I love that tweet. It's pretty old, but Okay, so what we're going to cover today, real quick, is we're going to figure out how training an animal works, right? Like if someone has pets and stuff, we're going to get to that. So how would you train an intelligent life form, right? So what exactly goes into thinking? Fluffy, yes. Aryan, yes. All right, so how would you train a machine, right? So once we try to sort of establish how training works with actual things that are alive, how would you train something that isn't alive, right? We just saw like a CPU is a rock with lightning, all that. It's a machine. So how do you make it think, right? Unless you're telling it what to do, how do you make it think? And then neural networks, which is just a fancy way, like, you know, that we like to express what AI looks like. And we're going to examine what exactly comprises an AI, right? Then we're going to cover some basic concepts. Do not fret. There is not much coding today, and there is like, the math concepts aren't that, you know, in depth today. Don't worry. You can explore them later if you want. All right. And then we are going to summarize how all these like building blocks go together. And then I will be providing you with some of many resources that you can use to further your passion for AI, your newfound passion. All right, let's get started with training an animal. First, does anyone have any questions? Even though like I didn't cover that much yet. Any questions? I am keeping an eye on the chat, or you can just use your mic. Okay, moving on. All right, so training a pet. How many of you guys have pets? Just like do the thumbs up thing with the emoticon thing on your screen if you have a pet. Any thumbs ups? Okay, cool. We have quite a few pet people. Does anyone want to volunteer and tell me how they trained their pet to do their first command, like, you know, sit or whatever? Does anyone want to tell me like what went into making them do the thing, the action? You can just raise your hand. 1 second. Okay, wait. Aryan says he will give me $50 if I can train his dog. I would be more than happy to take that up. All right, can somebody give me an example? If not, like I have my theoretical way of training a pet, but we'll get to that. Positive reinforcement, point at something. Okay, all right. So those are some, you know, pretty direct and reasonable ways to begin indicating to the pet that you want them to do something, right? It's like pretty standard. You know, you point to either like a ball if you want them to retrieve it, or you point to like their dinner bowl thing if you want them to like eat. I'm not sure. I don't own a pet. The closest thing I have is my brother. But essentially, here is how I would train a pet. And I'm just expressing this in Python because Sammy did Python last week, and I thought, you know, maybe it'd be good, like a sort of like a refresher. Suppose your command is fetch, right? While true, which is just a way of saying that you're just going to keep running this loop until you have a reason not to run it. If the pet doesn't understand your command, do not give it a treat. It's very sad times. If the pet does understand your command, give the treat, break out of the loop, and you have successfully trained the pet to understand your command. So that is, okay, I don't know if that's anything like what training a pet really is, but that's just how I would think about it, at least think about the process. It's a cute dog. Now think about a human, right? Think about like babies, which, I mean, honestly, we're still animals, but like our brains are some of the most complex things in biology. So how would you like figure out what's in this picture? Any volunteers on the mic, preferably, if not in the chat? Oh my God, no. Okay, wait. All right, just think about it. How would you figure out what's going on in the picture? What's in the picture? Any volunteers? No need to be shy. There's not much. Yes.
Someone would first have to tell you what it is, and then you would know it.
Right. Okay. but once someone told you what it was, and if you saw another one, how do you identify that as what they told you? What's the giveaway? What are the clues that lead you to that answer?
Uh, visual traits like the seeds or the little bush on top.
Great, that's perfect. Okay, that is literally it. So we call those features in ML and AI, but essentially that's what they are, right? They're traits. They're things that you can identify. They're giveaways to the label. Okay, so features include leaves, the little bush thing on top. There's a pointy tip at the bottom, right? That's something that you don't always find in every fruit. Grapes, apples, you don't see like pointy little, specific conical, whatever. There's seeds on the outside, like you pointed out. Not too many fruits have that. And a very shiny surface, right? Arguably, like there's other fruits with shiny surfaces, but moving on. So putting all of these together, we get some sort of answer, like someone said, right? Someone has to tell you firsthand, like what it is, and then you can always associate that later. So that's called the label. And these must be strawberries would be how we arrive at that answer. So that is how this would work, classification. All right, does anyone have any questions before moving on to training a machine? Okay, just gonna keep rolling. Oh wait, someone actually mentioned earlier, touch the fruit and examine it. So that's another kind of feature, right? That's another sense, another input. So that's definitely another way to learn about something. All right, training a machine, moving on. First of all, why AI? Right, first of all, like it's revolutionary. Like it's such a cliche thing to say about AI now because it's been around for a while, but it is changing the way that we approach problem solving. Because usually in typical programming, what you have to do is you have to tell the computer step by step what to think at which point in order to get like a result. You don't know the result, but you know the input and you know the method, right? So that's what you give the computer. And then the computer takes those two together. Wait a second. Can you guys see my thing?
Like the slides?
Yeah. Can you guys see the slides? Did
Yeah,
it
I can see it.
disappear? Okay. I was terrified. Okay. So yeah, you essentially in an AI, you just give it the input and output, and it has to figure out what's going on in between. So that is why it's revolutionary. You don't have to walk it through. Powerful, right? AI is capable of thinking about numbers and dimensions that the human mind can't stretch beyond, right? We can reasonably manage with 3, and we can sort of imagine 4. But in our heads, trying to visualize anything beyond that is kind of ridiculous. But in the case of an AI, you just go ahead and do the multiplication because AI doesn't care about visualizing. It can still get the answer just fine. But for humans, we like to spatially correlate things, which is why if you understand linear algebra, like AI is going to be a breeze because you're training yourself to think in dimensions without visualizing them. And you can just go up to like infinite dimensions that way. Finally, the last thing is AI. I mean, it's not the last thing. There's like a ton of reasons, but this is another important one. AI is autonomous, right? We don't need to tell the computer how to solve the problem anymore. Like I mentioned, you give it the input and output, it figures out what's in between. All right, so key skills for AI. I went through several websites, sources, and based on the people that work in the industry that I've talked to, here are some key things that just matter so much for when you're trying to be an ML engineer or whatever. First up, ML concepts, machine learning concepts, which includes predominantly math, right? It's math, statistics, and it's statistics, linear algebra, and calculus. Those are the 3 biggest areas that they tell everyone who's trying to learn about AI to focus on, because that is like linear algebra is just the way ML thinks. Statistics is the data science stuff that happens before going into a model. And then, calculus is like refining the AI. And we're going to get to that in a bit, but ML concepts, right? And then you have data science, pretty sort of like self-explanatory, but it's basically you need data science in order to give an AI the right data to think. And we're going to see some examples in a bit. And then you need to have some sort of medium to communicate with an AI programming. And right now it's Python. In the future, maybe it'll change, or maybe the way we use Python is going to change. But essentially, you need some way to implement these, abstract floating concepts. Yeah, that's like one of the sources. I think someone has their mic unmuted. Thank you guys for saying cool slides. I just heard you. Okay, wait. Someone's unmuted. Very strange. Okay. All right, we're gonna move on. So there's 3 main types of machine learning. All right. And the one that we're gonna be focusing on this semester is called supervised learning. Essentially, we just saw features and labels a little while ago. So you give the AI labeled data, right? The AI knows what the answer is and it knows what the input is. And then it has to figure out some sort of link, some sort of correlation between the features and the label. Over like a lot of training, it figures out if it sees those certain features in a strawberry, it's a strawberry. So that is what supervised learning. Unsupervised learning, you give data without labels. And the AI is like, I don't know what to call these, but these things look similar to one another. And that's why we use unsupervised learning to cluster things and identify patterns. Even though the AI can't name it, we can name it. We just need it to detect something that we might miss, because we can't process that much data like manually. And then there's reinforcement learning, creating real-time data from a live environment and deciding on the best action to take. Can anybody guess one pretty popular application of reinforcement learning in the chat or on your mic?
Isn't there like those like, I think Google made it. It's like a chess robot. It was like competing with competitive chess players.
That is it. That is literally it. Playing
Deep
games.
Blue, right?
That is, yeah, what?
Was it Deep Blue?
Deep Blue, yes. Deep Blue played chess. Even though like it wasn't strictly AI, it was more like a bunch of if-elses. That was like the first example of using an AI to play a game. But more recently, we had things like AlphaGo. We had things like OpenAI's Dota 2 playing bot, right? It just, I think the world champion was like Dendy or someone, and they were playing against this Dota 2 bot by OpenAI, and they got beaten, which is pretty cool. Also pretty sad, but pretty cool. I see some other, okay, games, cool. Stock market is epic. That is a great response, because it is something that you wouldn't think of when you think of like, real-time data, live environment. But that is what it is, because stocks keep going up and down, and you need to have some sort of way to identify what the next change in the stock value is going to be. That is a great way to use AI. Reinforcement learning. Google Dino Game, yeah, you can implement that. Super Mario, Jeopardy, Street Fighter, yeah, AlphaGo, documentary. I need to check that out. Okay, so that's that. All right, so now we have to talk about what exactly using an AI looks like. All right, so let's step into the shoes of Netflix. What does Netflix do? It's a recommendation engine, right? It just has this huge database of like a bunch of movies and TV shows and whatever. And our job is to try to identify what to give to whom, and try to identify whether they're going to watch our suggestion. So to begin that, we collect data. Over a lot of time, we collect a ton of data from different users, and we try to see if we can get users across all demographics, right? Some features here include things like age, things like time of day that they're watching. That might change what they're watching. Like I don't know if Netflix can detect how many people you're watching the show with, but I don't know if we could do that. That would be cool. Basically, there's like a lot of different features, right? How many days pass between one watch and the next watch for the same person. And then our group is to group together people who like similar things and then recommend certain shows. And if they like it, then we're going to be happy. If they don't like it, we have to do better. So what we do for that, we take this data, we split it up. We split it up into something called training data and test data. All right. So training data goes into an ML model, and then we're going to predict. Looking at that training data, we're going to say, this person is like 22 years old. And I think they're going to enjoy watching, I don't know, Brooklyn Nine-Nine, right? Something, I don't know. So I'm going to recommend this show to that person, and let's see if they click on it or they keep scrolling. The next step is to see what happens, right? Check the cost. If they did click on it, that means your recommendation was good. If they didn't click on it, then you need to do better at identifying what they want to watch. And then that means you have to optimize the basis on which you predict what they want to watch. That's an iterative process over like a ton of data. You just keep looking at people, looking at their tastes, and keep trying to refine your understanding of what they like. Once you're happy with a certain cost, which is like the error rate, right? Once you're happy with a certain level of that, you're saying, I am good at recommending stuff to this data set. Let me try this on some data that I haven't yet seen. So that's called unseen data or test data. And then you see if you can still perform like that without having data that you already know what the label is, right? So that is called test data. If you do well, you're ready for deployment. If you didn't do well, then you go back into training, right? And I think like a way that we could relate to this is basically if we look at ourselves and how we prepare for like tests. We have training data, which is like the homework problems in the book or like worksheets and all of that. We have the answers and we have to figure out how to get the answer, and we try to minimize how many mistakes we make. And then we go sit in the exam room, and then everything goes, you know, crap hits the ceiling, and we have to figure out whether we need to go back and learn more before the next exam and what we need to do differently before the next exam. So we go back into training, and then once we decide that we're actually done now, we're ready to go, we have the final model, and that goes into deployment, which means like businesses can use your recommendation engine to actually make recommendations. That whole phase is called training, and then this is called testing. Are there any questions so far? I'm sorry, that was a pretty dense slide. Are there any questions?
I have a question. So what do you mean by the check cost?
We're going to get to that in more detail later, but essentially checking cost is seeing whether your prediction that they were going to watch the show was right or wrong. And then over time, you're going to get better at recommending things that people do want to watch. So then your cost will go down. Does that make sense? Okay. I'm trying to see if there's anything. Okay. We're fine in the chat. All right. So TensorFlow Playground. I don't know if you guys have seen this, but it is so cool. All right. We're going to come back to this a bit later in the presentation, but essentially what we have here is an AI here in the middle of the screen. And we have a problem. The problem is we have dots of two different colors, and we need to figure out a way to separate them. All right, we need to get the blue dots together in one section of the screen, and we need to get the orange dots separate from the blue dots. So let me just run this with the stock settings. It does a fair job. It took a while, but it did it, right? It took 136 epochs. That just means it processed this whole data set 136 times before it figured out that this was the way to do it. And look at this little graph here. That is the cost. All right, it's also called loss, same thing. And you're basically changing little features inside, factors inside the machine to try to minimize that cost. You can change how much training data versus test data you want, which is cool. It's a slider. You can see the test data. The machine doesn't see these test data points, these extra dots. The machine doesn't train on those, but it still tries to classify them, which is why you can see two parts to that loss curve. If you don't follow what I'm saying, you will at the end. Even if you don't at that time, we can always talk later. All right, we can do funky things like mixing the dots up, making it harder for the thing to learn, right? It's still managing somewhat, but like it's not going to be 100%. And there's no way it can be, because the orange dots are like smack in the middle of the blue dots, right? So that it's doing a job, like a good job, but it's not able to do great. And that's why like the loss is still at 30%. We can change these things. These things are called neurons. We're going to get to them, but you can change how many layers of them we have or how many of each in a layer. We can change what features are going into the input layer, and it just over time it does a better and better job depending on whatever features you have. Look at that. That was so quick, and it took 19 epochs to drop the loss down to like 0.05%. No, 0.5%. All right. Like, try to remember these things because you'll see them in a bit, but don't worry about them too much right now. But that is it. That is how you can visualize an AI, and this is such a great tool for that. So that is it. We're going to get back to the slides. Neural networks. If you have any questions, just like stop me or like say it in the chat, or just wait until I say, do you have any questions?
So
All right.
could you go back to the TensorFlow for like 1 second?
Sure. What's up?
So I just want to clarify it. So
Yeah.
if you reset the, okay, you already reset it. So the dots that are already on the image, that's the training data?
Yes. Right now, this is the data that this AI is trying to classify. It cannot see these things. The hidden dots, that's unseen data. So it doesn't see those while training. It's like test questions. You
So
can't
just like,
figure out.
Okay,
Yeah.
so it takes test data and like decides where to put them?
Yeah, it is not looking at the test data at the moment, but essentially it's trying to solve two problems in one shot in this particular model. It's trying to solve for the training data and the test data based off what it learned on the training data alone. Does that make any sense?
Yeah, cool.
It's the same way that you use like your mind for like the worksheets as well as the test on the test day. But you don't know the answers to the test, but you do know your worksheet answers or whatever. Okay.
I have
Any
a
other
question.
questions? Yes.
So for that, is like the program's just trying to find like where the blue dots are?
Yeah, pretty much. It's trying to identify a way to like box them out from the orange dots. And we can change the data set, right? We can like do a circle. We can do this, this, or this. This one is pretty hard for this thing to solve. If you look at it, it sucks, right? Because like they're like one within another. But if we were to increase the number of features going into the input layer, right? The number of different things that it can detect, like in a strawberry, we could detect the leaf, we could detect the seeds, we could detect the shape. So these things can identify more patterns, and this should do a little better. All right. Okay. That is strange. Hang on. It's going down. It's going down. Okay. I don't know what it's doing, but yeah.
It's training too specifically to the data set.
Yeah.
And so the testing data, it's just getting random stuff.
Pretty much. It can't see the test data. It can't like learn from the test data, but it's learning only from the training data. What if you once you guys, oh my God. Okay, that's better, sort of. Okay, once you guys play with this, you'll probably like spend a whole hour just like messing with the. Okay, there we go. It sort of got a spiral sort of thing. All right, it's better. Okay, so the loss dropped. You guys will see the more you play with this, but it can get really fun. And yeah, any other questions?
What exactly does the loss what does the loss exactly mean in terms of this?
It means, in this case, it means the number of blue dots that are in the orange space or the number of orange dots in the blue space. Basically, the number of things that got wrong.
Okay.
And it's trying to minimize the number of dots that it misclassified.
Okay.
So if this curve, yeah, what?
Yeah, so like basically when the loss in general is just like what it couldn't classify and what it can.
Yes, exactly. The same thing with the Netflix recommendation engine, right? The loss is basically when you recommend something, but the person doesn't watch it. You just need to do better at recommending. That's the job of the model, the job of the AI. Does that make sense?
Yeah.
Cool. Okay, moving on. Neural network. So we're going to try to like understand what we just saw in the TensorFlow playground. But first, I just want to talk about the name, neural networks. Is anyone here a biology student? By any chance? Either now or in high school or whatever. Okay, if you are/were, you've probably seen something like that. And you probably can draw that way better than me, but essentially it is a bunch of neurons in the brain, the 86 billion thing at the start. Those are like the little units that do thinking inside our head, right? And how do they work? We call them neurons. They're linked through synapses, the little gaps in between these little branches, dendrites and whatever. They each receive something called a neurotransmitter, which is essentially an input. They each like see something, and then they release neurotransmitters, which like they do something, which they're passing the signal on to the next neuron. And that's how they work in the brain. So loosely based off of that, we have created this artificial neural network, which mimics that in these certain ways, but beyond that, similarities sort of end. Instead of neurons, we have nodes. We still call them neurons sometimes, but that's okay. We have nodes. They're linked through little connections called weights, right? And if every neuron in a layer is connected to every other neuron in the next two layers, it's called a fully connected layer or a dense layer. You'll see all sorts of terms later. Don't worry about the jargon yet. So each of them will receive an input number. It's a value. It's just a number. And then it's going to produce an output. The same way that these things receive and release neurotransmitters. Thank you for the compliment on the slides. So kind. Okay. So what is a neuron? At least in an AI sense. That's it. Thank you for coming. I'm going to stop sharing that. Okay. It is essentially a bucket in which you store a value. That is all it is. I could store any number in it. And how does it get that value? We're going to see in a bit, but it just stores a number. Now put a bunch of them together and we're going to see how. We have an image. All right. Suppose it's the strawberry image, but it's just, I just made it like fit the theme. And we need to figure out, thank you. We need to figure out if it's a strawberry or if it's like an apple or like some other fruit. We could do anything we wanted in the output layer. We need to figure out if this thing is a strawberry or an apple, just to keep things simple. So what do we need for that? Oh, yeah, that's called the output. What do we need for that? We need a few brain cells to which we can send this input. This is Google Slides. Thank you. Yeah, we need a few brain cells to which we send this image, right? And we do that through these connections called weights. And then we need a few more brain cells to process it. They're optional, but they can do the job. You know, if you increase the number of brain cells, you usually do a better job with bigger, like more complicated data. If you have too many brain cells, it just becomes dumb. And we're going to see that later in TensorFlow Playground again. I'll show you guys how too much brain is not a good thing. All right, so we connect these layers through these connections. We'll get to them. They're called weights. And we pass that information all the way to the output. And we somehow determine that we have strawberries in the picture. Are there any questions so far? It's just like a simple intro so far, but are there any questions? Feel free. There's no such thing as a wrong question or a dumb question.
Could you go back to the previous thing?
The previous slide?
Yeah.
Yeah. What's up?
So basically it takes features into input layer and processes it through to hidden however like intermediate layers are, and then
oh dear, someone's annotating. Someone's annotating. Okay. Yes, that is exactly what it does. It takes certain parts of the image in each of these input brain cells, right? And it tries to look at what it's seeing. That's deep. Look at what you're seeing. Okay. Does that answer your question?
Yeah. Cool.
Okay. Moving on to some basic AI concepts. This is not going to be too hard, especially if you've done like high school math, you're good. Even if you like, you know, you're not, math isn't your forte, you're still going to be fine. Don't worry. It's my responsibility to make sure. A linear equation. All right. You have some variable X, you have some output that you need to get from that X. What do you do to it to create a linear equation? Does anybody have the answer? In the chat or like
an equal sign would be a good start.
Amazing. Okay. All right. Along with the equal sign, something. Okay. A hint is it's sitting right next to the X.
It's a slope.
Y equals kx.
The slope. Yes. Great. So we have a slope. Okay. We call it M in math for some reason because M stands for slope. And then what else do we need? We don't need it, but it's a good idea.
Y-intercept.
Yes.
Y-intercept.
Plus
Perfect.
B.
Perfect. We need it. We need a y-intercept because that lets us change where the line is on the coordinate plane. If we didn't have this, we just always have it passing through the origin, which would kind of get boring, right? So that is why we have this y-intercept. That's a linear equation. Simple. Now we come to the idea of a function. I have some value z, and I need to get some output out of it. What do I do when I say something is a function of z? It's a dumb answer. Don't overthink it. Whoever wants to answer, just go ahead. What do you do to z when you're saying that I have a function of z?
Pass it into the function, get an output.
You put
Right.
z in the function.
Yes, you can do anything to z and you have a function of z. You can even do nothing to z and still have a function of z, right? This could be multiply by 1. This could be subtract z itself and you get 0 every time you do this function. So whatever you do, you're getting some sort of output by plugging z into the function. That's it. You guys are right. We're moving on to this concept. Do any questions before we start this? Because this is like super important. This slide. And the next one. Okay. Presuming that we're cool so far, suppose you have an input. All right. And suppose, let's say this input was a part of the picture in the strawberry image that we were trying to identify whether it's a strawberry or an apple. So this is a certain part of the picture. We can call it a pixel or whatever we want, but it's an input. And does anyone know how we can turn a pixel into a number? This is for like the comp sci people.
It's coordinates.
Coordinates?
Or RGB.
Color.
RGB, perfect, right. Essentially, it's like the scale. Coordinates is also part of the answer, but essentially you're trying to find out a numerical value that determines the color because images are just stored as a sequence of colors, right? You have the white separating the red in a strawberry or whatever. So here you have the RGB value. Hex code, I guess, also works. How does the coding fit into this? We're going to come to coding later. There's not much coding today, but you need this stuff if you want to like code an AI later. All right, so we need to know how much to let that input influence our prediction, right? And that's why we assign something called a weight. We're giving that input a weightage. If we drag this X from like the corner of the screen or the image, right, where there's no strawberry, then that isn't important in identifying what the strawberry is. So if we got the X from the middle of the screen, we probably want to give it more weightage so that we're like using that information better, right? It's like if someone said, what's the weather today? I don't know, but I'm having pasta for lunch. That's like irrelevant information. What's the weather like today? Well, it was rainy yesterday. That's a useful piece of information. So that is what weights do. They're influencing the prediction. You multiply them and you get X times W. You can optionally, just because you want some other parameter, or we're going to get to parameters, just because you want some other way to tweak your answer, you have something called a bias. All right. And at this point, we have this value Z, which is essentially XW plus B. All right. If it sounds too mathy at this moment, don't worry. We're going to try to tie it together later. And now here's something called an activation function. All right. Suppose that we have Z as any real number. It's just a number that could be like negative 2000. It could be positive 727.8, whatever. Right. But we need something specific from that number. We don't care what the actual value is. Suppose we care if it's positive or negative, right? So sort of like a binary way to split that number. So that's called an activation function. We're going to look at a couple in just a minute. And once you pass it through that function, that output is just called A because A stands for output. Yeah, that's it. Z is just XW plus B, which is like a linear equation. It's nothing more than that. And then you have some function, or you do something to Z, even if it's just nothing, right? A is the output. Here are the labels for this. W is weight, B is bias, and F is activation function. That is what goes on inside one node to get that 42, that little value, whatever it's a bucket for, that's what goes on in a node. Any questions so far? This slide had quite a bit in it. Okay. Okay, thank you for the past. Can the function be other functions apart from linear? You mean this function at the end? Because yes, the answer is yes for this function. Okay. Yeah, that function can be like a bunch of different things. We're going to look at a few common ones and a few like really important ones, but it can be anything. What is a weight again? Good question. A weight is nothing but a number that we use to determine how much that input should influence our prediction. All right. So suppose like, I mean, I could use the same example, right? My job as the network is supposed to predict what weather I'm going to have today. And someone comes by and says, I don't know, but here's what I had for lunch. That's probably not going to change the weather. So I don't need that information. So my weight in that case for that piece of information would be 0, ideally. And if if someone else came by and said, it was rainy yesterday, it was sunny the day before that, but it rained and it was like pouring last week. Those are all useful inputs. So you want to give that a higher weightage. So you multiply it by a bigger number, right? So like 500, because that's useful information. So X times that weight tells you collectively how much importance you're giving that X. What is a perceptron? A perceptron is nothing but if one node makes the whole AI, that's called a perceptron, right? So we can go back to that lovely diagram of a node. Hang on. If this thing was the whole AI, that's called a perceptron. So this is like the Lego block that goes into like building way bigger, more complicated AIs. Are we cool so far? Does that answer your question? Awesome. Okay, great. We're going to move on. I don't know what the time is. Oh, dear. All right. I think we're fine on time. That is a perceptron. And essentially, if one node was the whole AI, right? Here's the input. Here's the prediction. We're done. That is a whole AI. That's what we call a perceptron. Now, here's just a slightly more complicated example. Now, if we had 3 inputs, or how many ever inputs, we give each of them a different weightage depending on how relevant they are to what we're trying to predict. So again, in the strawberry picture, if X1 came from like the corner of the picture where there's no fruit at all in like that pixel, then it's useless. So we give that a low weight. X2 might be in the middle. X3 might be like towards like the tippy tip of the strawberry, which could give us information about whether like it's a tippy shaped fruit or like a round fruit or whatever. So we give each of these inputs a certain weightage, that like weighted average, if you guys have heard of that, that's what this is as well. It's pretty much that, right? So you take the weighted sum of your inputs. That Greek symbol sigma just means the sum of all of these individual products. We can add a bias if we want, just like a y-intercept in a linear equation. We can add it. It can be 0 if we don't want it, no problem. But we just need something else to tweak the range of values that we can get. And then we have some output z. And then we apply a function depending on what kind of output we want. We're going to get to this in a second. And we have a. All right, how do we determine the bias? We don't. This is something that the network controls. The neural network, or like this, in this case, just this one node, it can control what this bias is, and it can control what these weights are. And we're going to get to that. How does it autonomously control that? We're going to figure that out in a bit. Hang on. Yeah, it's simple to understand. If you understood what happened on the last slide, it's the same thing. Yeah, a weight, bias, and activation function. Those are the 3 key terms. Honestly, that's all you need to take away from these 2 slides. That's what happens in a node again. Activation functions. So why do we need them, first of all, right? Suppose my range of values in this case, hang on. Suppose my range of values on Z was like anything, negative infinity to positive infinity. I could have had any number. But if I wanted to determine whether something was going to be a yes or no, right? If my prediction problem was something like, is this customer going to leave in the next 30 days? That's a yes or no question. How do we determine that from 3,000 or like from negative 467? We don't have any meaningful information from that. But if we were to apply an activation function on that number, we would be able to determine like a yes or no equivalent by using something like this. It's called a step function in math, essentially. Okay, I saw someone say 10H. Yeah, we're gonna get to that. Yes, so this is a step function. Anything less than 0 becomes a 0 on the y-axis. Anything greater than 0 becomes a 1. So it's like turning it into a binary state. Whatever the number is, it's going to end up being a 0 or 1 after we're done with this activation function. Does that make sense? Are we all good?
As you said, activation function depends on what your Z is. If it's greater than or equal to 0, it's 1 or 0. But what do you mean by 1 or 0? Because, you know, when you talk about activation functions, you talk about practical applications. So, I mean, what is like there? What do you say? Significance.
Okay. So suppose, let's go back to the perceptron. Okay, now that you guys have seen this, we can go back to the perceptron. Suppose, I'm going to walk you through this in a different way. We have a few inputs, all right? Suppose you're a bank and you have a customer who's sort of been like kind of iffy about whether they want to do transactions with you because they don't like you or like your interest rate sucks for them or whatever. They're like doing less and less business with you. So you try to look for clues, the features that go in, right? What is their transaction history? How frequent have they transacted with you? Have they drawn any amount in the last 6 months? Or have they, you know, deposited anything? Or like, have they taken a loan? All of these are values for that. Okay, so far so good. Those are called features. Now you try to determine how important that feature is in figuring out if that person is going to leave you or not, right? So if this is like how many, I don't know, how many numbers they have, like cell phone numbers registered with you, that's not going to influence a lot, right? So the network might say, well, that's not a really important piece of data. I'm going to sort of ignore it by giving this weight a 0. And then the next thing might be like whether they have deposited any money. And that's something important. If they haven't deposited anything in the last 30 days, that means like they're probably not looking to use you as a way to store their money. I'm sorry if this is like such a businessy example, but this is what like the real world thrives on. It figures out, you know, with an ML model. You figure that out and you add your weights and biases in, and then you have some number. At the end of the day, this is a number. Like Z could be 400 or Z could be negative 60. What do you do with that? You need some way to say if they're going to leave you or not. So you apply a function on it that turns it into a 1 or 0, a yes or no, true or false, instead of saying 400 to negative 60 chance that they're going to leave. That doesn't mean anything. Does that make sense?
So essentially you're converting whatever inputs you get into, putting that into a function, which then gives you like a meaningful output. Like if you want, if he's going to continue or not. Okay.
Literally, that's it. You said it exactly right. It's a meaningful output out of a non-meaningful number. So that's what the activation function does. This is one example. We just saw it. The step function turns anything into a 0 or a 1, nothing in between. Here's another common one. People who might have worked with ML before might have seen this. This is called the sigmoid function. Essentially, it's like the step function in the sense that it goes from 0 to 1, but it also has a little range where it's like in between 0 and 1. It's useful in other types of problems. We don't need to get too far into it, but it is useful to not have a 0 or 1 all the time and have a small range where it's like in between. Here's another common one, ReLU, that stands for rectified linear unit. And essentially, you're just taking out the negative here. That's all you're doing. If something is negative 60, ignore it. If something is 400, keep it. Does that make sense so far? Yes? If anyone has any questions, please stop me. Okay. I will keep asking for questions like every so often. And then here's, yes.
Sorry, could you explain the ReLU function again?
ReLU, yes. Okay. ReLU does nothing but taking the maximum of 0 and that number. Suppose you have 40. What is the maximum between 0 and 40?
40.
So it keeps 40. That's it. What is the maximum between negative 60 and 0?
0. Okay.
So it keeps that. That's it. It cancels out all the negatives. Does that make sense?
Like,
Yeah.
what happens if you're given if you're given like minus 60 and minus 40 in that case?
If you, I mean, this activation function will only be working on one value at a time. But if you give negative 60, it'll return a 0.
Oh, okay, fine.
If you give it a positive 40, it keeps that positive 40 because it leaves positive numbers untouched. But it turns negative numbers into 0.
Oh,
So that's
okay,
why
fine.
they call it rectified, because they're getting rid of negative numbers, which is mean to poor negative numbers, but that's how it is. Okay, here's an important activation function. You don't see this everywhere in the network, but you only see this in the last layer, and this is why this is important. Okay, I'll go back to the slide in a bit. Suppose we have a vector. A vector is nothing but a way of taking multiple single values. That single value is called a scalar by itself. And a vector is when you group a bunch of them together, right? So suppose you have a vector holding the value 6 and 4. And you need to turn this into a probability. Something like the probability of that image being a strawberry or an apple. There's a function that does that, right? And that is called Softmax. I don't need to walk you through the math of it because you'll never need it these days. There's ways to abstract that. You can figure it out if you want because it's fun. But if you have some raw value of 6, some raw value of 4, and you need to determine whether the 6 indicates a strawberry or not, you pass it through Softmax. And it turns it into a 0.88 chance that what you're looking at is a strawberry. And then you can just take that and roll with it and say, here's a strawberry. Does that make sense? Is everyone on board? If there is a single person not on board, we will stop the ship to make sure they're cool with whatever we're doing. Are we doing fine? I wish I could see your lovely faces, my friends. That sounded creepy. Okay. This is Softmax. Now we're going to get to optimization, right? We saw how information flows forward through a perceptron or an AI, like the basic building block of an AI. And we're trying to see how it learns from that. Suppose it predicted strawberry was an apple. How does it learn to change itself? So it has a prediction, and we call that y prime, y hat, whatever we want, against the label y. So suppose it predicted apple, but the label was strawberry, right? So it computes the difference between them. In this case, it would be like 1 or something like that. We'd have some sort of difference. And we would see, the network would see what the difference is, and that's called the cost. We saw the cost in TensorFlow Playground, which was essentially how many blue dots it put in the orange section. We're going to go back to it if you don't remember, but that's what cost is. How many errors you made. And then it tries various weights and biases. Weights and biases are things that the network controls to try to get a better answer the next time around. That's how it learns. So based on this cost, it does a little calculus magic. We call that backpropagation, technical term. And it figures out the right weight and bias to get the right answer. And that way it minimizes the cost once it finds the right internal parameters, right? Once it tweaks its understanding of the image. And there are some algorithms that do this optimization. Here are 2 important ones. You only need to know of them. You can learn how they work if you wish. One is called ADAM, that's adaptive movement or adaptive moment. I'm sorry. And the other one is called root mean square propagation. This one, ADAM, is pretty common because it's like the best of all the other optimizers so far, but There might be better ones out there that we haven't found yet, but essentially these are how a machine learns, right? Weights and biases are called parameters. If it's called a parameter, the network itself can tweak it. If it's called a hyperparameter, which includes things like how many neurons or which activation function or what optimizer, right? Which one of these are optimization algorithms. These things are defined by the human that makes the AI. So that those are called hyperparameters because we're egoistic beings. That is, okay, just on a graph, just to quickly review, you have the cost and you have some weights and biases. You try different combinations, trial and error, see what leads to the lowest cost, which means the most accurate prediction. And then you keep that weight and bias set as your finished model for that data set. Did this make sense? I am checking the chat. Okay, if Adam is the best optimizer, why are the other optimizers used at all? That is a great question. Some of them do better on some specific problems, right? It's kind of like pulling out a scientific calculator for 2 + 2, right? Like 2 + 2 is overfitting. We're going to come to overfitting. But essentially, if you're using a scientific calculator to do 2 + 2, like why, right? You can just either do it in your head or just do a regular calculation. But if you needed to do like some sort of derivation or something, scientific calculator is probably going to do better. So Adam is just like, it has every functionality, but sometimes it's just not the best thing for the job. But yeah, that doesn't mean that it's the best thing everywhere. Like there might be other optimizers we haven't found yet that might do better. Any other questions on anything we've done so far?
Can you go over hyperparameters again?
Sure. So hyperparameters are things that we as humans can change about an AI, whereas parameters are things that the AI can change about itself, right? An AI cannot add a neuron or a brain cell essentially to itself. The same way that we cannot add a brain cell. Actually, do we add brain cells when we eat food? That might be. Okay, we do not manually add a brain cell, right? The same way, an AI cannot add a neuron to itself. But a human can come in and change the network so that it has a neuron, an extra neuron. And that's called a hyperparameter.
Oh, okay. Thank you.
Make sense?
Yeah.
Cool. Any other questions? We can lose brain cells. That is true. I speak from experience. Okay. We'll come to overfitting in a little bit, Vivek. I'm glad that you brought that up. Okay, we're going to summarize everything. If you have questions, again, stop me. Neural network summary. We have an image. We need to figure out if it's a strawberry or an apple. We pass it into some beginning brain cells. I have a question for you guys. Can anybody predict how many brain cells essentially are in the input layer? If this image was a 30 pixel by 30 pixel image, 30, how many neurons would we need to process this full image?
Wait, what'd you say were the dimensions again?
30 pixels by 30 pixels.
900.
900.
Perfect. Nice. Cool. Okay, that's it. 30 pixels by 30 pixels means you need 900 neurons, 1 per pixel. Assuming this image isn't colored. If it's monocolored, then you can use this. If you had 3 colors, you would have to change this here to a 3. So it would be 30 times 30 times 3, and that would be 2,700 neurons. We have other ways of dealing with color, but this is like a rudimentary way of understanding how images can be fed into a network. What are the 3 dots? That's just my way of saying that I was too lazy to draw 900 neurons. How about making an AI whose task is to adjust hyperparameters? That is such a great question. And I had this question myself when I was learning about this. There exist such things, but they're really obscure and they're like not reliable yet. Maybe someone has a reliable one and they just were too secretive about it. But yeah, like a meta tuning AI, right? An AI that could control something else's hyperparameters. But the question is,
problem with that, I guess, sorry,
yeah.
Rohit. The problem with that is like hyperparameter changes the output of the model, the accuracy of the model. But if you take an AI to change that, we won't be able to judge. Like the AI won't be able to judge the output.
Actually, it would be. I'd be happy to have a discussion about this later, but there is a way that it can. It's a fun question. That's how you get terminated. That is a fun question. It's something worth thinking about. Okay, so you take in the image through 900 neurons. You apply an activation function at every layer. It's optional, but it's just a good idea to do it. If you don't want an activation function, just say linear because you're just keeping every value the same. ReLU, you're just canceling out negative values, right? In this case, pixels can't have negative values. It can go between 0 to 256 and that's it. But we just like to keep ReLU in there just for fun. I don't know. Then we feed that data to the next set of brain cells. This is called a hidden or a dense layer. We change the number of neurons to whatever we want, and we set the activation function to whatever we want. ReLU is just good for these inner layers. And then we pass it to the output layer. And this is, since we're trying to figure out the probability that this is a strawberry and not an apple, we have something called Softmax that we saw. It just converts raw numbers into probabilities. And this thing, because this is white, this is gray, we're going to assume this lit up as a strawberry because it had a higher probability of being a strawberry. And if you see the weights, like I changed the thickness of certain weights just to give you like the idea that weights, you know, treat inputs with certain importance, and thinner weights treat inputs with less importance. So that is, oh wait, no, hang on. There's a little bit more on the slide. Okay. At that point, you reach the prediction and you see what the error was. In this case, there was no error, right? Strawberry, strawberry, you're good. This set of weights and biases, something's working fine. So you test on another image. And if you get apple for that next image, then you have to go back, change your change your parameters, because you're the network right now. You change your own parameters, your weights and biases, and try again with more images until you can reliably recognize strawberries as strawberries, apples as apples. Are we good on the slide? Any questions at the moment?
Yeah, so you have inputs and then you move to the hidden thing. So like, why do you reduce it to 100 rectified ReLUs? I mean, they call it rectified linear units. Is that what it's called?
Yeah,
Right.
the activation function is called rectified linear unit. Yes.
So like, why does it go down to 100? Like, don't quite understand that.
It's just nicer when you have data flowing. Like if you have a massive input layer, but you only have a 2 neuron long output layer, right? You have 900 input neurons, but you have only 2 at the end. It just seems like natural to include something that's in the middle between those two. You can go even bigger. You could have said 9,000 hidden neurons if you wanted, or you could have had more layers, more hidden layers. Instead of just 1 like here, you could have had 5. But there's disadvantages to having too many brain cells. That's called overfitting or underfitting. We're going to come to that when we go back to TensorFlow Playground. I'm sorry this is taking long, guys, but I'll be done in like 5 minutes. TensorFlow Playground again. Okay, so we just saw activation. We have, oh no, hang on, I need to refresh this. All right, why is it not working? Okay, you guys see this, right? We can change the activation function, linear, sigmoid, ReLU, tanh, whatever we want. Suppose we wanted to try sigmoid. It's not doing that great because it just isn't, it's just blue. Like there's nothing going on. So we probably need a few more brain cells, a few more inputs. Let's try this. Not working. Okay, let's keep it at ReLU and let's increase the training data. There we go. All right. So these are called hyperparameters. All of these things that we can change right now, including the features that we send in, the neurons in the middle, how many we want before we hit the output, and what activation, learning rate. Okay, one quick thing about learning rate. This is essentially how we like read through the textbook, right? If we have a very high learning rate, it's terrible. It doesn't know what to do. And the cost is like above 1, which shouldn't be possible. But essentially, it's like flipping through the textbook way too quick so that you don't learn anything from the textbook. But if you were to drop the learning rate to like a really small value, wait, let me refresh. If the learning rate was really small, it's like reading everything word for word. And by the time you're done with the chapter, someone else finished the exam, right? So you're learning way too slow. It'll work, but it's just going to waste a lot of computation. You can see the cost dropping, but it's just going to waste so many resources. So we try to find something that's like a good balance that does the job, you know? And by changing these, companies spend weeks and sometimes months getting the same model to do the job in the least possible epochs that they can. An epoch is, again, how many times you read a book from cover to cover. A batch is like a chapter. A bunch of batches make one epoch. A bunch of epochs are like how you train to understand a book better and better, like if you read it cover to cover again and again. So that's it. Please go play with TensorFlow Playground. It is fun. You are going to learn so much. Here's some resources. You can check out some articles about ML who probably explained it better than I have. But you have the TensorFlow tutorial. Keras is a high-level API in the words of Google. You don't need to know too much about it, but you can just like start using it as soon as you read a couple lines. It's really simple to understand if you follow the concepts that we discussed today. Google Colab is, Siddesh wanted to mention like a little thing about that in a second. Google Colab is what we're going to be using to build AIs this semester. TensorFlow Playground, here's a link. 3 Blue, 1 Brown. It's a YouTube channel with really, really nice explanations. I can put these links up on Discord, sure. Deep Learning Specialization on Coursera, that's the one that I did. You're more than welcome to do that or any other one if you have the time. It's worth it. Activation functions, like this website compares a bunch of activation functions and tells you like which is good for what job. Archive by Cornell is a repository of research papers, bleeding edge stuff that you can get from like Stanford, MIT. A bunch of universities put up stuff that, you know, they've been working on. You can check out research papers by them. Springwise is a website that lets you keep yourself updated on like tech revolutions and new tech and stuff. So next step, play with TensorFlow Playground. Just do it when you're bored. It's fun. It's captivating. Trying to get the best performance. Try to minimize how many epochs it takes to learn, right? Read some articles if you can. Read some research papers as well, if you really can, about ML. Maybe write a few TensorFlow lines, especially like, you know, because Keras is easy to understand. tf.keras. It's like, it's in the tutorial. But we will also be like sort of walking you through it before we begin the project this semester. I will mention these links in the Discord chat. No problem. I can get that. These slides are going to be up, by the way. You can just go to these slides and just click on them. Any final questions before we're done? Articles and papers about ML. I can look up some good ones and recommend some, sure. Any questions? A list pinned would be good. Sure. I will definitely be able to do that. No problem.
Okay. So guys, I'll take over from here and I'll discuss a bit of Colab with you.
Siddesh, I had one more thing, bro, before I
sure. Sorry.
pass the baton. A quick survey, just so that you guys can like help me understand if today was helpful or not. Or how it could have been better. Just I send it in the chat. Click on it. It'll take less than 60 seconds. And that's it. Thank you. Siddesh, I'm so sorry. Please continue.
Yeah, no problem.
Go ahead, buddy.
Yeah, I'm just sharing my screen. Okay. So I've given access to all of you guys in a shared drive. It's an unlimited storage, so you can use it for anything. But yeah, like you can use it for large data sets and all. But don't put personal stuff because UMD and all of us can see that it's not privacy protected. And then you can create new Colab files from here. If you can see my screen, that's the Google Collaboratory. So this is a practice and personal folder where you can create a new file and put it here. So this is one I'll just show you. Yeah, so this is a basic view of Colab, how it is. So each box here, it's a set of codes you can type, and then you can just press it and run it. And this set is another line, but the thing flows throughout. And if you have experience with Jupyter Lab or this is similar stuff, so this will help you. And yeah, so about putting your data in it. So if you can see the content, and then this is your terminal drive, and this is the shared drive with BigTh AI, which is us. You can put your data through this or your personal drive, whichever is fine with you. But I guess there's a limit on your personal drive, but there's no limit on our shared drive. And then put your stuff, your data in here, and you can just run. You have to change the directory. And when you change the directory, like I have this file in my personal drive, and this will load in a second. Oh, shit. Yeah, that's it. Runtime got the same thing. This is the main problem. So runtime is one thing. Like runtime is where your variables will be saved. So if your runtime gets disconnected, all your variables will be lost and all your present work will be lost. So please make sure to save it. And see, this is my personal drive, and all the files are loaded. And I'll just go ahead and read this Excel file into this, and like I can use the data. So we'll be going over with more about this in the next lecture, and I don't want to take much of your time. I guess if you have any questions like on the basics of Colab, just tell me, and I'll put up something. Yeah,
Colab.
I'll put something in detailed in on the Discord as well. Okay.
Feel free to stick around, ask questions about either Colab or, just anything that we talked about today, or even Python from last week, because Sammy's still here. Just like chat about, the sports usage of data analytics that we covered today in the discussion section by Sagar and Tanmay.
And yeah, do tell me like if you get the access, or if you are not in the shared drive, I'll just put you in and share me your top mail IDs if you haven't done so yet. Share your top link, Sagar.
Thank you. Thank you for the slides. Thank you for coming. Those who are saying thank you in chat.
Thank you all for coming. It was,
super fun.
It's really fun when we have a lot of people around.
Yeah, pretty big, lovely crowd today.
Yeah, I actually didn't expect that many people to come to the discussion, to be honest, but they did.
Sagar, bro, you were on fire earlier today.
What, man? I was like, I was thinking about the worst, but turned out to be better. Yeah.
Bro, full NBA lecture mode. What a man.
I mean, if they knew about Madrid and all, I would have gone on a 1 hour lecture about why Madrid's the best club in the planet.
I was gonna ask, where did that go?
Okay, Sagar, you also have that.
Oh, I have it? Okay, cool. Right.
Yeah.
Rohit.
One sec, I have to go. I'll see you guys later.
I guess
good job,
Jai
bro.
is not
Sammy.
All right, guys. See you later.
All right, Roti, good job.
See you. Thank you.
Yeah,
Want to stop recording?
Yeah.
Sammy, what's up? You
Oh, you want to stop recording?
Oh, right. Yeah.
Yeah, I'll tell you.